Hey guys! Right, what's up? What's up, Zach? Is this the one? Yes, this is the one, Ryan. This is the one. Right, guys, I'm going to crack straight on. I'm so glad that my singing happy birthday to Don wasn't actually recorded. So glad about that. Whew. Found it, boys. Right, I'm going to close down that window, but I've got the popped out chat, which is amazing. There we go. Winner. Everyone's appearing. Cool. Share screen. Boom, boom, boom. And we're in. So I'm going to then choose this guy. What I'm also now going to do is I think I'm also going to turn off my camera. Now, I don't know whether you guys were there for that when I did that and it crashed my laptop. But I'm going to give it a go because my laptop's running a little bit slow today. Hello. Oh, no, gone Yorkshire. Gone Yorkshire already. Oh, no. Love a good bit of Yorkshire. Bit of Yorkshire. Hello, disable device. Don't crash. Don't crash. Winner. Excellent. That means my laptop will run a little bit better. Just a little bit. And it makes a difference, actually. Right, guys, today's learning objectives. So we've like, this is going to be a nice speedy lesson. So today's lesson, we're looking at measuring rates. Now, you probably noticed that I've got lots of questions set up on the right-hand side. But here's our title for today. So this is measuring rates of reaction. We've got 3 learning objectives today. So we're going to be Yorkshire accent is the best. Is the best. I can try and do a Welsh accent. How about Welsh? Not very good at Welsh, though. Methods of measuring rates. No, you see, it turns into Jamaican. It's an absolute nightmare. I'm just going to stick with Yorkshire. Okay, methods of measuring rates, gas collection in particular. Then you got thiosulfate plus HCl reaction. Got to know that guy. LXL, love that reaction. Don't know that. Oh, Welsh is also nice. Rate units. Okay, so first thing we need to do, folks, switch back to the good old English accent. I'm trying to do a British accent. Hello. Sorry, let's do methods. So we've got subtitle, methods of measuring rates. Methods of measuring rates. So, measuring rates. Now, there's actually loads of these. Like, there's loads of different methods for being able to measure rates. However, there are particular methods which are easier than others. So, for example, if we do just a couple of reaction examples. So I'll just underline that. So reactions. Let's just look at a couple of reactions here. So we've got number 1, e.g. I'm gonna try my best to e.g. number 1. Let's do zinc plus hydrochloric acid. Now, zinc is always a 2+, by the way. You've got to know that, guys. Zinc is always +2. So you can now pause the video and have a go at completing that equation for me. And then unpause it when you're done. So this is a metal plus acid reaction. We're going to form salt and hydrogen. So in this reaction, if we then do state symbols, zinc, of course, is a metal, so it's solid. All acids are aqueous. All salts are aqueous too. And then the gas is, of course, in salt. The only time, by the way, I shouldn't say that. I take that back. Not all salts are aqueous. You need to know your solubility rules, and we'll come to those later. Mercury, lead, silver, or all the halides, sulfates, and carbonates, they're all insoluble. But in this case, it's soluble. So what this means is during the reaction, there's something which stands out, and that something is the hydrogen gas. Yeah, we're going to be producing a gas. Now, this is really easy to measure. If you ever make a gas, this is a nota bene. I'll do this in red. If a reaction ever makes a gas, nota bene, reactions producing gases, we would always measure rate by collecting that gas. It's a very easy method by collecting gas. Now, there's 2 methods of doing gas collection. So the method number 1 we're going to talk about. So we can now do method 1. Method 1 is gas collection. And this is the most common method of measuring rates by Edexcel. Now, collecting gases, there are actually 2 methods. So method A is called fluid displacement. fluid displacement. So what we're going to do is now this is where you guys get to see my amazing drawing. Oh, look, there's the drawing over there. There's one of the gas collections. Yeah, but this one's fluid displacement. I should move my questions over. They're just a bit too close. Gives me a bit more space. I've just grabbed Edexcel questions, by the way. I just went on and look, there's the fluid displacement one. I'm going to have a go at drawing that now. You guys, by the way, are expected to be able to draw these, just so you know. Wow, I grabbed an awful lot of questions on rates. Oh, there's the thiosulfate reaction. Good old Edexcel and its thiosulfate. Just going to move all these. Oh, move all these over. There we go. Gives me a bit more space. That's better. So method A, and I'm going to attempt to draw it. It's always good to try and draw these things. Fluid displacement, I'd like you to do the same. So what we're going to do is we're going to put the reaction into a conical flask. Yeah, conical flask. There we go. And we're going to add our acid. And then we're going to add to that, let's call this HCl, and then we're going to add our zinc solid. Yeah, there's our zinc solid. So in this, we're actually adding a zinc chip is what we're adding. Yeah, a zinc chip. Now, once that's in and reacting, I'm going to start producing hydrogen gas. Then what I'm going to do is I'm going to seal it with a bung. Seal it with a bung. And then I'm going to collect the gas underwater. Do the best I can. There we go. So now I'm going to collect this underwater. My trough's going to leak. Measuring cylinder. And I'm going to collect the gas underneath the measuring cylinder. Now, they've done these diagrams so many times, so that's the picture there. Now, just to tell you that this diagram makes an appearance in Edexcel an awful lot. Now, can I just say that this practical is fraught with problems, but there is a top problem with this. So, problems with this practical. Yeah, problem number one, our survey said top answer. Yeah, this is our top answer. Yeah, gases are soluble. Gases are soluble. Now, you need to know two particular gases that are soluble. And those ones that are very soluble include, yeah, gases are soluble, especially CO2 and SO2. Just to also tell you that the hydrochloric acid is as well. Yeah, but those two commonly appear by Edexcel. So we're going to be making, by the way, you notice that hydrogen isn't in this list. Hydrogen is not particularly soluble, but it is a little bit. So gases are soluble. What that means is, as a result of this, I'm going to change my color to green. Yeah, as a result, volume of gas collected is less than expected. They always ask these questions. Yeah. So fluid displacement. Now, now can I just point out there is a second problem. Problem number two is that there is a delay between adding solid and sealing bung. And sealing bung. There you go, sealing bung. What that means is the result of this is that you lose gas at the beginning. Loss of gas at start of reaction. At start of reaction, so less gas than expected. So less gas than expected. It's clever problems. Now this one, I do love this question because this problem, because there's actually a solution to it. And that solution to this problem, and I'm going to do this one in red. Yeah, there is a solution. Chemistry has all the solutions. So the solution, by the way, you can see it over here. There's their version. Yeah, and they've going to have had that problem, definitely. But there is a solution to this. That solution is this, is when you set up the conical flask, what you do is you add your liquid and then you place inside it another beaker. and that beaker has your solid in it. Then you can add your bung. You can add it. You can collect underwater if you wish. There we go. Get the point? So you can add this, and then what you do is a really clever trick. So you put a beaker in it with your solid, and then you shake. Shake it like a conical flask. Oh my God, I should never have said that live on YouTube. Oh, so bad. Oh man, it's terrible. Never saying that again. So when you shake or rock the flask, or rock, you're gonna rock it up in chemistry. So when we rock the flask, this falls over and the solid drops out into the acid. Yeah. So a nice easy fix. There are other versions of this this fix. So other ones include what they'll do is instead of doing the beaker, what they'll do is they'll add a piece of cotton string, and on the end of it they tie with a little ribbon. They tie the solid and they trap the string in between the cork. And what that means is all they have to do is just lift up the cork a little bit. The solid drops in and you've got plenty of time to then put it back on before it hits the water. Yeah. So it's quite clever, that one. I do like that one. Another one, by the way, this one is not actually a thing, but there is another one. This is one of my students invented this, and it was actually allowed. So he said to have a magnetic shelf. So he's got a magnet here, a magnet, and then he had a metal shelf that he then put his solid on. Now, just to let you know that actually isn't allowed. The reason being is the metal might react with the acid. But what he was super clever, and what he did was he covered, oh no, I don't know what I've done. I've changed my pen type and I don't know how I've done it. Oh no, I deleted it. Oh no. I deleted it. Add. Oh no. Pen. Oh no. I'm stuck. All right, ruined it. Anyway, so what he did was he had a metal shelf, and when he took the magnet away, oh no. When he took the magnet away, it would drop in. Now, what he did was he actually covered the metal shelf in plastic, and so it was allowed. Clever plastic coating. That one I thought was Jesus. That was genius. Plastic coating. It's really clever. And as I said, it was allowed. Just because you set up the little shelf, put your... Anyway, I'll stop. So this is method number 1 for gas collection. And what you do is you just measure the volume of gas collected every 30 seconds. Yeah, not complicated. Okay, method number 2, and the preferred method, yeah, is gas syringe. Yeah, method 2. Method 2 is gas syringe. This is far better. Yeah, so gas syringe, again, you do need to be able to draw this. They have asked it in the past. There we go. Let's add my little rocky, let's add my little Nabika with my solid in it. There we go. And I can add this. This is far better practical in terms of gas collection. By the way, to get the mark, you had for the gas syringe, you had to show the scale, had to show the little lines on it. There we go. There's the gas syringe. Seal that. There we go. Cool. And this one's far better. Now, the same issue applies in terms of loss of gas. They've done lots of fun questions with all of these. So, for example, when the syringe was set to 0, yeah, there is still air in both the conical flask and the tube. So why does that not matter in terms of gas collection? The reason being is the gas being produced simply displaces the air that's already in the system, so you're still getting a correct measurement. But it does mean that your final sample at the end is impure. You can, they've asked that one as well, so you always get an impure sample of gas whenever you do this practical, but you're not trying to measure you're not trying to sample the gas. What you're trying to do is you're trying to measure the volume made per unit time. So that one, it's fine to do that. So gas syringe, this is a better method than fluid displacement. You don't have the issue of soluble gases. Displacement. Right. So at this point, I'm just going to mention data. Yeah. So what they'll do is they'll collect the data. Yeah. The data for this would be, they would have, let's say we're going to change the concentration of the acid. Yeah. Conc of acid, moles per dm cubed. There's my units. Yeah. And then so we're going to have something like 1, 2, 3, 4, and 5. And then we're going to have volume of gas collected. Yeah, vol of gas collected in 60 seconds, let's say, in 60 seconds. So that would be something like 60, let's repeat it 3 times. Yeah, so we get 60, 59, and 61. And then we get something like concentration 2, we're going to get more. Yeah, so we're going to get 70, 72, and 58, and then 82, and then 84, and 80, and then you kind of get the point. We'll just stop at that point. So at this point, the reason why I'm doing this is because I'm mentioning anomalous data. Yeah, just what they're going to do is they're going to ask you to calculate the average, and just be aware that you need to be able to spot data that doesn't fit the pattern. These are fine. Yeah, but the reason why we know that that one's anomalous is because that number there is smaller than the previous experiment. It cannot be correct for the higher concentration. So you ignore that data. This would be add them all together and divide by 3. This is add these 2 and divide by 2. This one would be add all 3 together and divide by 3. So just mentioning data collection and anomalous data at this point. Okay, so we've covered gas collection. Okay, so what other ways of measuring rate are there? Okay, so the next one is I'm going to mention the thiosulfate one. Yeah, so I'll also mention time for, so okay, so method, okay, so the problem is I put method 1 and 2 for the gas collection, and then I should have done A and B. Oh yeah, method B. I'll just do B, gas collection. That's better. Right, method number 2. Okay. Method 2, yeah, and this is, let me show you the reaction for this. We will do, let's take carbon dioxide gas. We're going to bubble that through lime water. Now, this is super useful. Yeah, Zach, having spoken to you, Zach, about the entrance exam you're going to have to take, this is one of the things that you'll have to pick up is the limestone cycle. Technically, it's not on Edexcel, but you're going to need to know it for your exam. So this is lime water, calcium hydroxide. Yeah, and what's going to happen is we know that when you blow into lime water, it turns cloudy. So it's going to form calcium carbonate, which is a solid, and water. Right. Now, the key here to this one is, so before, what we were spotting the gaseous state symbol. Yeah, but now what we're spotting is the solid state symbol. This is solid or precipitate. Now, so what's going to happen is this is going to turn cloudy. We remember this, I hate that word. It forms a white precipitate of limestone. So what we can now do is we can measure the rate of this experiment. Now, this is actually considered what's called a non-continuous rate measurement. The reason being is what we're going to do is we're going to set up a conical flask. We're going to add our lime water. There we go, calcium hydroxide, aqueous. There we go. And then what's going to happen is we're going to then bubble through. We're going to use another reaction to generate CO2, or we're just going to bubble in carbon dioxide. Yeah, so I'm just going to go. And by the way, key thing, bubble through lime water. Yeah, that's actually really important. Test for carbon dioxide. Bubble through lime water. Yeah, CO2 going in. Right, what we're going to do is we're going to measure this rate. Now, what's going to happen is it's going to turn cloudy. So what's it going to turn? It's going to become like this. This is where my diagrams are letting me down. What I'm going to do is I'm going to move down a bit. There we go. I'm going to do that way. Diagrams letting me down. It's going to turn opaque. Yeah, so it's going to become like this. It's not going to be yellow though. It's going to be white. So I'll choose gray. It's going to become opaque. Now, what you do in this scenario, if you're ever making a solid, what you can do is you can use what's called a cross method. So underneath the conical flask, this is where what I'm going to do is I'm going to now turn my conical flasks into 3 dimensions. So I'm going to turn my conical flask into 3D, like this. And underneath the conical flask, I'm going to add a piece of paper. I'm going to add a piece of paper. And on that piece of paper, I'm going to draw a nice dark black cross. Like this. Now, what's going to happen is as this becomes more and more cloudy, the cross is going to disappear. Sorry about the quality of my diagrams, folks. I do apologize. Yeah, I'm going to draw a nice dark black cross. And as it becomes cloudy, eventually what's going to happen is it's going to become opaque. And I'm going to stop being able to see the cross. And then I know when to stop the reaction. There we go. So I can't see, and I can watch this. Yeah, there we go. So I can watch this and time how long it takes for the cross to disappear. Yeah, I can time how long it takes for the cross to disappear. Now, this is a non-continuous method. What that means is you're not going to be able to plot a graph from this. You could plot a graph if you do multiple experiments in terms of how long it takes the cross to disappear, but you can't plot a graph from a single experiment because you're going to get a fixed amount of time. You're going to get one time, and that's the time in which it takes for the cross to vanish. Now, this method has a limitation. So this method, nota bene on this method, it is a non-continuous method. I'm going to switch that to red and then switch that to black. So nota bene. This is a non-continuous. Continuous means you can just take it, like the numbers are just continuing and you can take it every second. Non-continuous method of measuring rates. But also, yeah, there's only one value. And what that means is it changes the rate equation. Yeah, one time. Now, because it's only a single time, it means that the only thing you're going to be able to calculate is the average rate. Average rate. You can't see how the rate's going to change over time. You're just going to get the average rate through the whole experiment. So now this method also gives us a really unusual rate equation. Because rate, we remember from the last lesson, that rate is change in the concentration of product over change in time. Now, the issue is, usually, we can measure things like in the gas collection method. This is really easy. This works super well for this. The reason being is I can work out the change in the concentration of product is going to be the change in gas volume. And the change in gas volume, of course, is just going to be from 0 to, yeah, and then, so let's say to 50, yeah, and I can just work out the difference. If it started at 10, yeah, it's 40. So I can work out a change in product, because the gas, I can measure it before and afterwards because I'm actually taking a measurement. And of course, change in time, that's easy. But now in this case, I'm not actually measuring the amount of product. The amount of product is fixed. Amount of product. The amount of product to make the cross, the X, disappear. And the great thing is we don't actually have a number for this, so we can just call it 1. And that is a very odd thing. Edexcel love this. The rate becomes 1 over T because it's a fixed amount of product. It's a rather unusual thing to see, and this only occurs in this particular, well, it actually can occur in others. It can occur in color change experiments as well. Another example is called the iodine clock. I'm tempted to show you that one. Yeah, I'm going to show you that. Now, I'm streaming to YouTube already. This is going to be interesting. Is it worth it? No. Guys, have a look at the iodine clock experiments. And you can realize that this equation here also used for iodine clock. Have a watch of the video. It's really cool because it's a sudden color change, which means you can't measure anything. There's no continuous numbers. It's just, it's there, it's not there, which means it becomes 1 over t. Okay, so at this point, I've got 10 minutes left. I just want to show you some questions that have been, oh, there's a third method, method number 3. Method number 3. Method 3, mass change. Mass change. Okay, so this method is very, very straightforward. Let's do limestone plus sulfuric acid. Pause the video, complete the equation. That's a solid, that's aqueous. I'm going to form calcium sulfate. Calcium sulfate. It is soluble, not very much, but it is. Plus CO2 plus water. Right, so we've got 2 choices here. Straight away, we've seen the gas symbol. So method of choice would be gas syringe. However, what happens if you haven't got a gas syringe? There's an alternative. You can do what's called mass change method. And what you do is you take your conical flask and you sit it on top of a set of scales. And all you do is once the reaction's going, once the reaction starts, by the way, I'm going to put some cotton wool in the top. The reason for the cotton wool, just to let you know, the cotton wool will allow the gas to leave. It will allow the gas to escape, the CO2 gas. Yeah, but what it won't allow to escape is any water that's splashing from this. The water would be soaked up into the cotton wool, and then so it doesn't decrease the mass. Yeah. And what's going to happen here is simply the mass is going to drop. Yeah, mass decreases. And you can read the mass off every 30 seconds or every 10 seconds if you like. Mass decrease, and this is a continuous method like the gas syringe. Continuous method. And we can just monitor it. Now, the reason why this is a special one and why it's different is because it changes the graph. Because in the gas syringe one, the graph is very clear, because what happens is as time progresses, time on the bottom, in minutes or seconds, what's going to happen is the volume of CO2, this is vol of CO2, and what's going to happen is we're going to get a lovely increase graph like that, and there's our rate graph. Yeah, but on the mass change one, you realize the graph does exactly the opposite. As time goes on, the mass of reaction is actually going to decrease with time. Yeah, it's the exact opposite. Now, I'm doing rate graphs next lesson, so I'll talk to you some more about these next time. Now, it's 10:15. That actually brings me to the end of my lesson. I just quickly want to run through some questions super quick. So question number 1, they've given us a mass change one. There's the cotton wool. And it shows you the mass change. The graph shows the results. Oh, I haven't actually kept the questions. That's ridiculous. Maybe, hang on, have I? 16, no, I've seemed to have lost my questions. I feel like I've made a mistake there. It's totally possible. Let's go to the next one. Just to quickly do a few. So, okay, what would happen to the graph if I increase the concentration of acid? The mass is going to decrease more quickly. Yeah, and I might actually get more CO2 given off as well, depending on which one's in excess. Does it say? Excess of hydrochloric acid. So we're actually going to make exactly the same amount. We're going to make the same amount, but faster. There we go. I need to end at the same point. There we go. So it decreased quicker, faster rate. Yeah, decreased quicker than the first one. Yeah, but I made exactly the same amount because the acid was in excess, which means the limestone was the limitation. If let's say what else do we want to do with this? Let's decrease the temperature. If we decrease the temperature of this, what's going to happen? I'm going to make the gas slower, and it's going to end later. So it ended here before because it's gone level. Now I'm going to end there. So I'm going to, there we go. Oh, no, hang on a sec. hang on, the lower temperature, I'm going to make the same amount. So I'm just going to end later on. But I'm going to get the same amount. It's clever, that. Yeah, rate graphs are tricky. I'm going to spend a bit of time doing those next lesson. Right, the hydrogen peroxide and a catalyst reaction, I'm assuming. Yeah, state two properties of the solution that should be kept the same. Its volume and its concentration. What solid does not seem to act as a catalyst? B, hasn't done anything. Seems reasonable. Which solid is the most effective catalyst? Time to collect 100 centimeters cubed of oxygen. That's a trick. Everyone's going to go for A, and the answer is D, because they only took 11 seconds to make 100 centimeters cubed of gas of oxygen gas. So D is the best catalyst, the least amount of time. Clever, that. In the first experiment, the student added 1 gram of A. Describe what he could do with the contents of the flask at the end of the experiment. Show the catalyst was not used up. Weigh it before and weigh it afterwards. It'll still weigh 1 gram. Collecting gases. Right, what have they done? The table shows how the student wrote down their results. I used 6 marble chips. One also says the teacher said that she could only use the results from student 1 because the others had not recorded enough information. Identify the piece of information the student failed to record. In my experiment, there were 6 marble chips. Okay, 80% hydrochloric acid. Okay. I collected 100 centimeters cubed of volume. We've got concentration. Where's the vol? No volume for number 2. The marble chips in 6 formed 100. They haven't counted the number of marble chips. I used 40% hydrochloric and 6 marble chips. They haven't done the volume again. Oh, hang on a minute. It took to collect gas. They're missing 2 things. They haven't given us the vol of acid and they haven't given us the vol of gas. Haven't got either. I collected 100 centimeters when I used 6 marble chips. No concentration of acid, no vol of acid. Both missing. Clever, that. I like it. Why can the student no longer see the cross at the end of each experiment? Because we're forming solid sulfur, which is opaque. Next. Why is it important that students add the water before the experiment? They're doing a dilution, guys. So they're doing the reaction between hydrochloric acid and the thiosulfate. Well, and they're trying to dilute it by adding water. You should always add the water before the acid, because otherwise the reaction will start before the dilution's been done. So you'll get an incorrect number. Sulfur dioxide gas is given off in a reaction. What precautions do you take? Sulfur dioxide is toxic. So the precaution is a fume cupboard. The explanation is it's toxic. So I've just gone through a couple of questions just to show you these kind of things and how they appear in the exams. It's nice to see all 3 methods making an appearance as well, which is nice. I'm going to end the lesson there today, guys. I'm just going to check my learning objectives. So number 1 number 1, methods of reaction and collecting gases. We're fine. Thiosulfate reaction, we've covered it. We talked about how it forms solid sulfur and this rather odd cross experiment. We've missed rate units. So we'll pick that up next lesson. So guys, I will end my stream there. I hope you found it useful. So I'm just going to go, I turned off my camera, haven't I? Device manager. Enable device. Should come back on, there we go. And then I can start camera. There we go. Right, guys, I hope you found it useful. I will see you guys next lesson. You have a measuring rates homework, which I'll post on the classroom, and I'll see you guys next lesson. See you later.